In this video, we are going to discuss about scaling. So what is scaling of the MOS transistor means? So it is nothing but reducing the critical parameter of the device. Okay, in accordance with the given criterion, in order to improve some performance features like increasing the speed of the circuit and reducing the power dissipations, then increasing the number of gates on the chips, then minimizing the feature size, then maximizing the operational frequencies, then it will reduces the production cost and die size, okay, and so on, by keeping the basic operation characteristics unchanged. So the advantage of the scaling in the MOSFET is packaging density, right? So if I reduce the size of the transistor, I can accommodate more number of transistors. There will be more space, so I can accommodate more transistor, thereby the packaging density get increases. Okay, and the size of the chip. So as we can see, the packaging more number of transistor in the same space, hence we can decrease the overall area of the chip. Okay. Next, multifunction of chips. So since the transistor size get reduced, we can make multifunctional chips, okay, by reducing the area of the chips. So these is called as these several indicators are called as figure of merits. Okay, that is a minimum feature size, power dissipation, maximum operation frequencies, production, reducing the production cost, and it comes under the figure of merit. So the figure of merit get improved by shrinking the dimension of the transistors, interconnections, and separation between the features, and by adjusting the doping levels and supply voltage. Okay. So what are the types of scaling is? So scaling can be classified into three major categories. First one is constant field scaling. That is here it is electric field it represents. Okay, so it is also called as full scaling. Then second one is constant scaling and constant voltage scaling. Third one is lateral scaling. Okay. So in this all all the parameter of the MOSFET is scaled down. To understand it in a better way, we will consider a case. Suppose the scaling factor is S. Okay, so if the scaling factor is greater than 1, so here the S values should be greater than 1. Okay, so if the S value is 1 means the L bar is same as L. If the S value is greater than 1 means the L bar get reduced, right? So so you can see the all the parameters of the MOSFET is scaled by the scaling factor is S. Okay, so the parameter value get changed to a new value. So okay, so if the L is original value, after scaling it becomes L bar. So first let us discuss about constant voltage scaling. So here what it represents, the physical parameter of the MOSFETs are scaled down, such as length. So the length of the MOSFET is decreased. Okay, so which will result in the short channel effect. Okay, so which will directly affect the drain current. So therefore the drain current is inversely proportional to the gate light. So if you see the value of IDS, okay, so what is IDS? IDS is equal to beta. So beta is nothing but mu Cox W by L. Okay, so if length of the transistors get reduced, it will directly affect the current of the drain current, and it is inversely proportional. Okay, so and all the parameters are kept constant, such as terminal voltage is kept constant. Okay, so the V is same. Okay, so the V bar is equal to V here, voltage. So voltage has to be represented in capital V. So V bar is equal to V. So it is called as constant voltage scaling, right? So next let us come to full scaling. So here the voltage and oxide thickness is scaled by 1 by beta, and resistance is scaled by 1 by alpha. Okay. So first let us discuss area. So area is equal to area bar, I can write as A into, so area is nothing but length into width, right? So area is nothing but length into width, okay, by alpha square. So this I can write it as L bar into W bar, where L bar is nothing but L by alpha, and W bar is nothing but W by alpha. Okay, and if you see Cox is nothing but if you see what is Cox? Cox is nothing but epsilon naught by Tox. Okay, there is nothing but epsilon naught bar divided by Tox bar. So Tox I can write it as there is nothing but epsilon naught x. Epsilon naught x bar is nothing but epsilon naught x. Tox bar I can write it as since Tox bar is nothing but Tox by beta. So I can write beta into Cox. Okay. Next gate capacitance. Okay. So gate capacitance I can write it as C naught bar W bar L bar. So okay, this W bar L bar I can write it as Cox by W bar L bar I can write it as WL by alpha square. Okay, WL by alpha square, and Cox bar I can write it as beta into Cox. So, okay, so I can write it as beta by alpha square Cg. Okay, so next parasitic capacitance. The parasitic capacitance is proportional to area and distance. Okay, so here the area is divided by alpha square. Okay, so the area bar I can write as A by alpha square, and D bar I can write as D by alpha. Okay, so it is representing either the length or width. So this alpha and alpha get cancelled out, so I can write Cx bar is equal to Cx divided by alpha. Next Q by A I can write it as it is nothing but the carrier density in the channel, so that is equal to Q divided by A divided by alpha square. So Q bar I can write it as Q bar is equal to CV bar, right? So C, here the C represents CG. Okay, so CG bar I can write it as beta alpha square into CG, and V bar I can write it as since V the voltage is divided by 1 by beta, I can write this 1 divided by beta into V. Okay, so here alpha and alpha square get cancelled out, and betas get cancelled out. So this is nothing but QA. Next, a gate delay. So gate delay I can write it as R into C. Okay, so R bar into CG bar. So R I can write it as V by I. Okay, so CG I can write it as beta by alpha square CG, and this V by I can write it as V bar I bar I can write it as V by I. So this is nothing but beta alpha square into R on CG. Okay. Next, operating frequency. Okay, so the operating frequency is nothing but 1 by T, right? So 1 by T. So T means a delay. So inverse of this one. Okay, so I can write it as alpha square by beta into F. So next, current, IDS, drain current, IDS bar. So there is nothing but, you can see it is nothing but mu n Cox W by L, and VGS minus VT whole square. So Cox I can write it as a beta into Cox. Okay, beta into Cox, and W by L I can write it as so W by alpha, and so W by L and W by L get cancelled out. Okay, so how to write the voltage? So voltage is divided by beta, right? So here you can see Cox I can write it as Cox I can write it as beta into Cox. Okay, Cox bar I can write it as beta into Cox, and W by L get cancelled out. Okay, and instead of voltage I can substitute as 1 by beta square, okay, into VGS minus VT the whole square. So here the beta and beta square get cancelled out, so you'll get 1 by beta. So this is nothing but 1 by beta into IDS. Okay. So next, current density. So current density is nothing but I by A bar. So this is 1 divided by beta into I from here, and A I can write as 1 by alpha A divided by alpha square. Okay, so like you can write as alpha square by beta into J. Next, energy. So energy I can write it as CL bar VDD bar the whole square divided by 2. Okay. So how to write CL? CL is nothing but beta by alpha square CL, and VDD I can write as VDD square, that is 1 divided by beta square into VDD. Okay, so here beta and beta get cancelled out, so it is nothing but CL VDD by 2. Okay. Wait. Next, power spectral density. So power dissipation. So the power dissipation in the transistor I can write it as so this is nothing but PG, right? So this is nothing but PG. So energy divided by time. Okay, so the energy is nothing but 1 divided by PG divided by alpha square into beta, and time I can write it as time from here I can write it as beta beta by alpha square. So here so we substitute beta by alpha square so you will get a beta by alpha square by beta. Okay, so since power bar is equal to energy divided by time. Okay, so the energy is nothing but 1 divided by alpha square beta. So this is frequency. So frequency I can write it as alpha square divided by beta. So if you solve, you will get 1 divided by beta square into Pg. So next, power dissipation per unit area. So you have to divide the Pg by Pg bar by A bar. So you will get 1 divided by beta square divided by 1 divided by alpha square. So you will get alpha square by beta square. Next, power into speed product or power delay. So the power into time. So what is the power value? Power value is power dissipation in the transistor, nothing but 1 divided by beta square, and TD is nothing but beta into alpha square. So the beta, when beta get cancelled, so we'll get 1 divided by beta alpha square Pg into TB. So for the constant field scaling, the alpha is equal to beta. Okay. So for the constant voltage scaling, beta is equal to 1. I have already derived the value of A bar, right? So A bar is equal to A divided by alpha square. So that is nothing but, this is nothing but gate area. So the A bar here represents the scaling value of area, gate area. Okay. So for constant field scaling, alpha is equal to beta. And for constant voltage scaling, beta becomes 1. So I can write A bar is equal to A divided by alpha square or A divided by beta square. If I substitute, instead of alpha, if I substitute beta, okay, I will get A divided by beta square. Okay. So I have scaled by alpha square or beta square, the gate area. Okay. So in constant voltage scaling, beta value is 1. So it will remain as same. Okay. So here I am not having any area. So here also it is same as A bar is equal to A divided by alpha square. Next, gate capacitance per unit area, that is represented as Cox bar or C naught bar, that is equal to beta into C naught, which we have already discussed, right? So you can see, so here Cox bar is equal to beta into Cox, right? So it may be written as beta C naught or alpha C naught. Okay. So it is better to write in terms of alpha. Okay. So if you write it in terms of alpha, you will get. So you don't consider beta value. Okay. A divided by alpha square or C naught bar is equal to alpha into C naught. Okay. So similarly, Cox bar is equal to C naught. You can substitute beta value is 1, right? So it is equal to C naught or C naught or Cox. So next, gate capacitance. So Cg bar is nothing but beta into beta divided by alpha square into Cg. So here if I substitute beta value is alpha, I will get 1 divided by alpha into Cg. For constant voltage scaling, beta value is 1, so Cg divided by alpha square you will get. Next, parasitic capacitance, that can be written as Cx bar, that is equal to Cx divided by alpha. So, okay. You can also write it as Cx divided by beta, but here it is not necessary. So both are same here. So you don't have any beta, right? So it is same. better you can remove this one too. So next, carrier density in the channel. So that is represented by Q on bar, that is equal to Q on. Okay, so for both of them the same. Okay, next gate delay. Gate delay I can write it as beta divided by alpha square into alpha. So if I substitute instead of beta, if I substitute alpha, I will get alpha into tau. Okay. So if I substitute 1, I will get alpha tau bar is equal to tau divided by alpha square. So next, maximum operating frequency. So f naught bar is equal to 1 divided by tau bar. So that is inverse of this one. Okay, alpha square divided by beta into f. So if I substitute instead of beta, I will substitute alpha, I will get 1 divided by alpha into f. So if I substitute 1, I will get alpha square into f for constant voltage scaling. So next one is current. Current IDS bar is equal to 1 divided by beta into IDS. So here you have to substitute instead of beta, you have to substitute alpha, 1 divided by alpha. So if I substitute 1, I will get IDS bar is equal to IDS. Next, current density. So current density is current divided by area. So IDS is nothing but 1 divided by beta into I. Area is nothing but 1 divided by alpha square into A from the first value. So if you solve, you will get alpha square divided by beta into J. So if I substitute instead of beta, if I substitute alpha, I will get alpha into J. Okay. So if I substitute 1, I will get alpha square into J. Next, switching energy per gate. So energy I can write it as 1 divided by alpha square 1 divided by alpha square beta into E. So if I substitute alpha for beta, I will get 1 divided by alpha 3 into E. So if I substitute 1, I will get 1 divided by alpha squared into E. Next, power dissipation per gate. So PG bar is equal to 1 divided by beta square into PG. So here you can substitute alpha, beta is equal to alpha. So PG bar is equal to PG divided by alpha square. And PG bar is equal to PG for the constant voltage scaling. Next one, power dissipation per unit area. So PA, that is represented PA bar, that is equal to alpha square divided by beta square into PG. So if I substitute beta equal to alpha, both get cancelled out. So PA bar is equal to PG. And if I substitute PB, beta is equal to 1, I will get PA bar is equal to alpha square PG. Next, power speed product. So PT bar is equal to 1 divided by alpha square beta into PT. So if I substitute beta equal to alpha, I will get 1 divided by alpha 3 into PT. So if I substitute 1, beta T bar is equal to 1 divided by alpha square PT. Next, resistance. So R bar is equal to beta by R bar is equal to R divided by beta. So that I can write it as R bar is equal to R divided by alpha for constant electric field scaling, and R bar is equal to R for constant voltage scaling. So in the constant voltage scaling, the drain current density and the power density are increased. So if you see drain current density, so it is increased by alpha value, you can see, compared to the constant electric field field. So which may eventually causes a serious reliability problem for the scaled transistors such as electron migrations, hot carrier degradation, oxide breakdowns, and electrical overstress. So in constant voltage scaling, all dimensions of the MOSFETs are reduced by the factor of S, but the power supply VD, right, VDD, and the terminal voltage like VD, S, VGS, VT and all remains unchanged. So these are the problems while doing the scaling. So the effects of SiO2 thickness. Okay, so on scaling this TOX, that is oxide thickness, eventually a stage will reach when eventually a stage will reach when the oxide will lose its dielectric property. Okay. Next is subthreshold current. For smaller devices, in addition to the VGS, the VDS also has a greater influence on the carrier flow in the channel. The carrier flow in the channel can be increased by increasing the VDS voltage, and also the potential barrier can be reduced even when VGS value is less than VT. So thus the resulting current through the channel for the higher value of VDS is called as subthreshold current. The next problem is noise problem. The scaling process which will results in the noise problem, which will degrade the reliability of the high density chips. Next, lateral scaling. So in this type of scaling, only the width of the gate channel is scaled. Okay, so it's commonly called as gate shrink. This type of scaling is used only in the specific applications. The disadvantage of associated with this type is high electric field through the channel, and hence it's also called as it also causes a short channel effect. So if you see the full scaling technique attempt to preserve the magnitude of the internal electric field in the MOSFET. So while the dimensions are scaled by down by the factor of S. Okay, so the full scaling, the power supply and the terminal voltage are scaled down proportionally with device dimensions. So, but the scaling of the voltage may not be very practical in many cases. In particular with the peripheral and interface circuitry, which may require certain voltage level for all the inputs and output voltages, which in turn would necessitate multiple power supply voltage and complicated level shifter arrangement. So hence for this reason only the constant voltage scaling is usually preferred over the full voltage scaling. So what they are telling is in the voltage scaling, the voltage is kept as constant. So in many of the cases, the voltage should not get reduced. But in the full scaling, what they are doing is they are scaling the voltage levels. So which will result in the which will result in the complication in the circuit, and it may not be practical in many cases. So that is why they used to prefer the constant voltage scaling over the full scaling. Okay, so this one is called as these column is called as combined field, that is electric and voltage scaling. Okay.